All right, welcome to the next video in the series where we are building a Pinball 2.0 kit. In this case, it's a Bally Evel Knievel using a reproduction Bally playfield. If you watched the last video, we were working on installing all of the lighting, which means these serial RGB lighting for the inserts, as well as the GI lighting around the edge. You'll probably notice that there's a lot of blue tape here that's sort of holding down our current wiring. That's only temporary because in the next step we're going to be installing the driver boards and the playfields that'll have the connections for our switches and our coils. And we're not going to lock down this wiring just yet until we have those other things in place. And then ideally those wires coming from switches will sort of follow the same paths, and then we'll start doing the tie down. All right, but first I want to talk a little bit about the strategy of the architecture as it relates to our hardware drivers. All right, if you follow some of my previous videos with my other builds, you'll know that I usually design my games so that it directly matches the way the vintage Ballys were wired up. So in theory, you can not only drop in a new playfield that you built, but you could also drop in a vintage playfield and play that game without changing any of the wiring, using the same code and everything else. There's no hardware modifications. All right, what we're doing slightly different this time, because this is a kit and we're using these fast hardware. I use the fast hardware in my other games, but because this is a kit that other people are going to be building as well, hopefully, I'm going to try to follow the architecture that the fast team prefers, which is to say they prefer to have the drivers mounted directly on the playfield. So instead of having a wiring harness for a switch matrix going off the playfield and into the cabinet and then into the drivers, they prefer to have these drivers mounted directly on the board. Now, in my situation, I have something like 25 different playfields, and so it's really not economically feasible to put, $600 worth of hardware on every single playfield. And it also doesn't really allow for vintage machines to plug into the same system. But this is more like how a professional pinball game would be made, where there's, by today's standards, a lot of the hardware is actually on the playfield. All right, so this is the method that we're going to use, but it's going to change a little bit our strategy on how we wire things up. All right, so the biggest change is going to be that our switches are going to be direct wired to each driver board. And by driver board, I mean this board is a set of switches and coil drivers. It comes in a couple of flavors. This one's called a 1616. This one's called a 3208. And what that means is 3208 means you have 32 switch inputs and 8 coil drivers. 1616, you have 16 switch inputs and 16 coil drivers. And these are going to be direct wired. So what that means is we're going to be wiring each switch is going to go directly to a board. All right. At this point, let's go back and look at our documentation of how many switches and how many coils we have in the game and figure out which combination of drivers we want to mount on the playfield. Okay, before we dive into the schematic, there's one caveat, which is we or I have decided we're going to use a trough on this particular example, and this is optional. You don't have to cut the hole for the trough. You could just use the single ball trough that the game usually comes with. But in this case, we're using this trough, and the standard trough has 6 switches for the balls. It's a 6-ball trough. It has an additional switch for a jammed ball, and then these boards are also designed to have a switch for the auto launcher, because if you have a multi-ball trough, you're going to want an auto launcher to do multi-ball. And the switch from here actually plugs into this board, and then this has a bank of all 8 of those switches coming out from there. All right, so this trough is going to sit right about there. The auto launcher sits here. And what I like to do for troughs is Fast also makes an 0804, meaning 8 switches and 4 coils. So that's kind of exactly what we need for this. And because you may or may not use this, I'd like to keep it sort of as a set. So the trough has a coil, the auto launcher has a coil, and we have 8 switches. So that means we've got everything we need here plus 2 additional coil drivers. And what I would like to do is sort of mount this near the trough, and usually aim this way. And so these switches are, that's the coils. Switches are here. Make a little cable that goes from here to here, and then we're all set. All right, so we can place this board right about here, and then focus on everything else is going to be somewhat standard based on the existing schematics. Okay, so Evel Knievel, if we look at the schematic for the switches, so Evel Knievel, most older Bally games had 5 driver lines and 8 receive lines for their switch matrix, which would normally be 40 switches, but you can see that what they're actually doing is they're not using one column of their switch driver, and so you end up with a maximum of 32 switches. In fact, we're not even using all 32 switches. If you look at the switch matrix, there's a few gaps, even if you're looking at just the 32 that are available. Now, also in the schematic, we see that the number of coils we have 1, 2, skip the out hole, 3, 4, 5, 6, 7, 8, 9 coils. And if we look at our options here for boards, we have a 3208 and a 1616. So in this particular case, a 3208 will work because we have just under 32 switches. We have just over 8 coils, but we can use the extra coils we have from this one. And one caveat here is that ideally you want the switch and the coil for auto fire to be on the same driver board, and that's going to mean the bumpers we want to be auto fire, and the slingshots we want to be auto fire, and the flippers as well. So right off the bat, that's 7 coils. The ones that are not auto fire are going to be the saucer and the drop target reset. So that's probably what we'll put on this one, saucer, drop target reset on this one, because these don't have to be auto fire. And then everything else will go onto this guy. All right, I want to add here is that this might be a rare case because Evel Knievel doesn't have a ton of stuff on it. Most games I would require having a combination of, I like a combination of the 3208 and the 1616 because that ends up giving you 48 switches, which is kind of what the max is for ballet. And then you have plenty of coils. And let's look at a different game, like if we were looking at Medusa. Medusa, you look at their switch matrix, they actually have 6 columns driving in 8 lines. So that's 48 switches right there for Medusa. And there are a ton of coils on Medusa. Like there's even there's a 7-bank drop target with memory. So right off the bat, that's 8 coils. So in that case, you would definitely need 2 boards at least. And the combination I like to have would be a 3208 and a 1616. And then also a separate, an 0804 separate. All right, but we're looking at Evel Knievel. So we can get away with just the 3208 plus the 0804. And now the question is, where do we place these to get optimum wire routing? All right, so we know what driver boards are going to go on the playfield. We have our 3208, our 0804. We also have an expansion board to drive our serial LEDs, RGB LEDs. You'll notice I have these brackets here. My preference for this is that they mount vertically because it's a smaller footprint. And I'll include the file for these brackets if you want. Now it is a smaller footprint, but you'll also notice that there's going to be some additional room needed for wiring plugging in, but that's going to happen at a different level than the LEDs here. So we're not at risk of interfering there. And so we end up with a smaller, tighter overall package. Okay, for this one, as I mentioned, I like this area because we only have to go from here to here. You'll notice I also have, the other thing I'm going to do is I'm going to put a terminal block or barrier block to distribute power. And I'm doing that here and also one here. Now the idea is that we're going to be running our coil wires to this location. This is the switched ground and this is the power. The thing that I don't want to do, and I suggest that you don't do, is we don't want to sort of daisy chain the power from coil to coil, because that's going to end up having, if you have separate lines for power and ground, you're going to end up creating some pretty large loops. That's not really best practice for electromagnetic interference reasons. You want to run power and ground wires as close together, and so what we're going to do is we're going to run these wires to this area here, and the ground will go to this board and the power will go to this terminal block. So they'll be as close together for as long as possible. And then we're going to be pulling power from another distribution board here. We'll bring power in here, and then we'll run that power and ground to here and then over to here. All right, so we're just going to put some screws in through here. What I like for this is I'm going to put it sort of as far back this way as possible without interfering with this wiring, and we're kind of in between. One leg of this bracket is in between these two LEDs, and we're sort of off to this side so that we have extra room for our terminal block here, and they'll be slightly closer together. When these connections come in, they'll just sort of split off and go this way. All right, so again, 3/8 inch number 6 And we can just drive it straight in here. And this is 3D printed, so don't do it too tight. Alright, so I'm going to put in these other two, and I'm going to do the same for this guy over here. Okay, for the terminal block, we're going to do the same thing. I usually put a screw on either side, but these are going to be 1/2 inch. And you can see, because we've got an extra 3/16 there, so we're about another 3/16 into the wood. Okay, so 1/2 inch screw will put us in a good position, and this is about where we want it. Let me just drive that in there. Okay, you only need 2 screws for that, and then I'll do the same over here. Alright, so the other board is going to be this expansion board for our LED driver. There's an option to put it here. I think that's going to be a little tight. I think this is better. And I want to be as far away from these coils as possible, so I'm going to kind of put it right about there. The other thing is that our starting point for a lot of our serial LED chains is right in this area. Now it looks like I did make one slight mistake here, because I would have been better off to have this go this way, and for some reason I had it start here and go this way. So what I'll do is I'll update the mapping, and then I'll just switch these white wires from in to out. I'll make those out and in, and I'll switch that along the chain there. But I'll update in the documentation, because it makes more sense to have this come, if this board's going here, it makes more sense to have the chain start here and go this way. Everything else looks good, because we're coming in here, here, and you're coming in here. All right. Okay, you could probably make a nice little bracket to hold this, but I'm okay to just screw this down directly. Just a number 6 should fit through this hole. Not too tight, because it's sitting up a little bit, and if you go down too tight, you're going to probably crack the board. So in theory, you should have some kind of spacer. You should have a spacer that lifts it off slightly, so that you could tighten it down without risking breaking the board. But right now I'm going to go for that. Alright, so now I'll switch these wires, and then we'll talk about hooking up our switches and our solenoid. Alright, now for wiring up the coils, I typically don't use IDC type connectors for other applications, but in this case, because the header is already installed and it has a friction lock, there aren't a lot of other great options that match this type of connector in the crimp style. And so I think that in this case, this insulation displacement type connector is going to be just as good as anything else that we could find. So we're going to use this for the coils. This is a 12-pin, 18-gauge connector. And then for similar reasons, we're going to do the same thing for the signal. This is 22-gauge, and this one is an 11-pin connector. And I'll link part numbers for these in the documentation. All right, because of logistics, I'm gonna skip. Normally, I would do the coils first. I'm gonna skip that first, and then we're gonna do the signal lines. And also, I will show you the way this works. In order to make this sort of connection, there's a tool you can buy, and basically it's as simple as you just put the wire in here and you push that down. And then we'll go over that part as well. All right, the other thing is I like to use these little 3D printed brackets. These are sort of like wire ladders, but this is a much sort of like a squatter version of a wire ladder. I don't like typical wire ladders you find. I think they're a little bit too flimsy and they sit up too high. In reality, we only need to separate a few bundles of wires, and this can handle 4 different bundles at 2 different heights. And I like this better just because it's a little bit lower profile, a little bit tighter, and we don't need like a really giant flimsy wire ladder. So I'm going to use this, and I'll also include a link to this file if you want to use that. And as we start building out our wiring harness, we will start to put these in places where we need to. Like for instance, to get over here, we're going to want to secure the wires like right about here, and then bring them over and into these connections. And we'll put these in different places on the board as we start building up our wire harness. Now, one last thing before we get started is because we're no longer using a switch matrix, so that means that it doesn't really make sense anymore to try to keep to the standard Bally switch matrix wiring, because we're not trying to make this cross compatible anymore because it's a different architecture now. But we do need to keep track of where our wires are going to go. And in our situation, it makes sense to try to group the wires in groups of 8, because we still have, they're still grouped in 8, and we have 4 banks of 8. And this is a case where we can actually sort of daisy chain the ground part of the signal. So it works to our benefit to group the switches in ways that are relatively close together. We're not going to have the same situation as we do with the coils, where we're at risk of either generating EMI or being sensitive to EMI with these switches. So I'm okay to daisy chain these grounds. But we want to keep those wiring as short as possible. All right. So in this case, you can see we'd probably want to put, what I'm thinking is, we have 1, 2, 3, 4, 5, 6 here, and we're probably going to want to have an extra switch connection for the flippers somewhere in this area. So we'll reserve the 2 extra for the flippers. That'll be one group. Another group will be here. We have like 1, 2, 3, 4, 5, 6, and then the 2 spinners makes 8. And then as we get up into here, we have 1, 2, 3, 4, 5, 6, 7, or 6. 6 switches up here, and then that'll be one bank, and then the last bank is going to be this drop target here, which has 5 drop targets plus a stand up in the back. All right, so that'll be how we break it down, and now we'll actually get into the actual wiring. Okay, similar to how we did our lighting wiring, we're going to basically lay out the length of wire that we think we want. And you notice that I'm sort of following our existing wiring path. And I'm just going to cut it to that length. So this wire will go from here to here. And if you notice on this switch, the input of this switch is in the middle, and you have normally open and normally closed on either side. Also notice that there's no diode on this one. Normally we would add a diode if this were going to be part of a switch matrix. There's no diode because it's a direct switch, So like in this case of the stand-up, there's already a diode on there. Instead of wiring to this pole, we're going to actually wire to the opposite side directly. Another thing about this, the way these switches work, is that the microprocessor has a pull up on the input. And what we're doing when we switch this is we're switching to ground, which is why ground is going to be our center pole. And then when the microprocessor detects ground, that pin gets grounded, that's considered a closed switch. All right. Okay, so very similar to how we did our lighting. We're basically going to strip our wire. We have our soldering station with us. Actually, I misspoke on these switches. I just checked. I was wondering about that. I just checked. It's actually the far pin is the common, and then normally open would be the center pin, and normally closed is the far pin. All right, so we're going to put ground on the far pin, sorry, on the near pin, and then our signal is going to be in the middle pin. All right, so ground here, signal here. Okay, so we 10 our pins. Again, I've just double checked, and this is common. This one on the end here. And then the middle is going to be normally open, which is what we want. Then we 10 our wires. All right, and then we just reheat this to get it soldered to that pin. Let that cool. Come back and do this one. Let that cool. All right. And now this sort of up down is our service loop, and then our wire is going to look like this. And as I go around, I'm going to continue to put like little pieces of tape on here to hold this down until we're ready to get it tightened up. All right, I'm going to continue to do this process all the way through to this end here. One thing to notice here is that I've wired in both of these switches on the slingshot mech, one here, one here. And when we bring the signal in, we're going to bring that signal the same way. We're going to bring it to here and then also bring it to here. So these two switches will be in parallel, and the closure of either one of those will then activate the slingshot the way it does on a traditional machine.